Okay, now we're going to continue in this lesson with margin of error, and this is going to kind of wrap up our margin of error area of the course here, looking at population means now, not population proportions, population means, okay? And then we're going to bring back the population proportions and do some real life examples, looking at some newspaper articles and stuff. So we're going to start off with our formula now for the standard deviation of a distribution of sample means. So this is when we have actual data, not proportions. All right, so you might just take a sample of anything. It could be heights, weights, shoe sizes. In this case, example 1, we saw this example similar to it in our last lesson. The course project in a computer science class was to create 100 computer games of various levels of difficulty that had ratings on a scale from 1 easy to 20 difficult. Suppose a random sample of 10 created computer games produced the following ratings. So let's see what's going on here. We have 100 computer games that were created, trying to figure out the difficulty level 1 through 20. We took a random sample, one random sample of 10. So it could be any 10. It could be game 2, game 6, game 50, game 70, all right? But only 10 of them. Random sample of 10 out of 100. And there's the actual ratings. So this isn't a yes or no question. This isn't heads or tails, yes or no, true or false, and getting a proportion. This is the actual ratings themselves. 12, 5, 2, 4, 1, 4, 18, 10, 1, 16. There they are right there. Okay? Estimate the population mean rating and find the sample standard deviation based on these 10 sampled ratings. So I'm just going to have you write down how to do this. This is where you do the 1 var stats. So if you had to do this, if you had a calculator with you, you would use 1 var stats. Okay? And you would actually put that on your exam paper if you had to do this. To show your work or what you're doing. But I did this for you ahead of time. X bar is 7.3. That's the mean of the sample. And SX is the sample standard deviation, 6.273. Did this ahead of time. Again, you would just put everything in list 1 var stats, list 1 and then blank, no frequency on this one. This is the average of the ratings, and this is the standard deviation. It's a pretty big standard deviation because it's a small sample, very small sample, and it goes from 1 to 50. It goes from 1 to 18. So can't really tell much. So pretty big deviation there. Use the formula given above to calculate the approximate standard deviation of the distribution of sample means. Round your answer to the 3 decimal places. So this formula is going to help us get the standard deviation of the distribution of sample means if you were to do more samples. Okay, so if you were to do more samples, and we're taking it from 1 sample. So the way we're going to do that is we're going to take it's S over radical n. So this is using 1 single sample. S is 6.273. And n is the sample size. And the sample size was only 10. So over the square root of 10. And this is going to give us our standard deviation for the distribution of sample means. If you were to do a bunch of samples, what would the standard deviation be? And it is 1.984. 1.984 is our standard deviation of the sample means. Standard deviation of sample means. So if you took a bunch of sample averages and distributed them, showed the dot plot or whatever, the standard deviation, the spread of that would be 1.984. So now we're going to do margin of error. Recall that margin of error is twice the standard deviation. So what is the margin of error here? Okay, well, here is our standard deviation of the sample means. We're going to do 2 times that, 2 times 1.984, and that's going to give us 3.968. So that is our margin of error. Okay, our margin of error is 3.968. Write a sentence interpreting the value of the margin of error in the context of this problem on computer game ratings. So what does the margin of error mean? The margin of error is, again, helps create an interval from the estimated mean of 7.3. So remember, we had 7.3. I'm going to actually do part E first. 7.3 plus the margin of error, 3.968. 7.3 minus 3.968. That is going to give us, let's see, 11.268. And subtracting gives us 3.332. Okay, so what we could say here is this is an interval that's likely to contain the population average rating. Okay, but write a sentence interpreting the value of the margin of error in the context of this problem on computer game rating. So we're going to say the population mean rating is likely to be within 3.968 of our sample mean. Okay? The population mean is likely to be within 3.968 of our sample mean. So in part E, we're going to add 3.968 and subtract 3.968, and we get this window right here. We get 3.332 to 11.268. That is the likely window of a video game rating. So that's not saying much. I mean, that's a pretty big window, 3 to 11. Remember, they can only rank from 1 to 20, right? But we're saying the average is likely to be between 3 and 11. It's not likely to be between 12 and 16. It's likely to have a very easy rating, right? Somewhere between 3 and 11 is on the easier end. So we can kind of tell that the likely average rating is between 3 and 11. All right, so we're going to kind of put that in words. We'll call them plausible values. So we'll say plausible, there's that word again, plausible values for the population mean are from, and you just got to write this again, from there to there. Okay, plausible values for the population mean are from 3.332 to 11.268. So the population mean likely falls in that window. It doesn't have to. It may be 3.2. It may be 11.5. But it's highly unlikely that it is that high or that low, because we took that margin of error and we added it to both sides of the mean, and it gave us a nice window to work with. Okay. So now, a summary of what we learned about margin of error. When you have proportions, and that means question, yes or no, true or false, heads or tails. What proportion of red chips do I pull out? If I pull out 10 out of 50, remember we did that one, 10 out of 50 red chips? That's 0.2. Those are proportions. When you're dealing with proportions, you have to use this formula that you need to memorize. This is the margin of error formula for proportions, sample proportions. When we have sample means, like actual data, like what we just did right there, it's 2 times S over radical N, where S is the standard deviation of the sample. And we're going to do a couple examples, one of each. Real life examples here. So this is evaluating reports based on data from a sample. This example 2 is using proportions. What proportion or what percent votes for a Republican governor over a Democrat, or Democrat over a Republican? If you go to example 3 real quick, it's talking about the number of chocolate chips in a bag, okay? And that's talking about how many chips there were. All right, that's a number of chocolate chips, so that's an actual data value. That's the difference between this guy and this guy. So let's do it. You'll see how it works. I think the more you do it, the more you'll get it. So the following is part of an article that appeared in a newspaper or online, right? With the election for governor still more than a year away, a new poll shows the race is already close. The Republican governor has 47% of the vote, and Democratic challenger had 45% in a poll released Tuesday of 800 registered voters. So it was a sample size of 800, not very big, right? That's within the poll's margin of error of 3.5 percentage points, making it essentially a toss-up, said the poll's director. So they're saying it's really a toss-up. Even though the Republican governor had 47% and the Democrat was 45%, because of that 3.5 percentage point margin of error, they're saying it's a toss-up. So let's talk about a few things about this here. First of all, why don't the two percentages add up to 100? Why is it 47 and 45? Well, that's only 92%, right? So there's another 8% left over. Think about that. Why could that 8% be? Well, hopefully you came up with either undecided voters, or a third-party candidate, like an independent candidate. They're not a Republican, they're not a governor, they're voting for somebody else. Or they're just undecided. They don't want either one, right? So that's the 8%. That's an easy question, I think. What is meant by the margin of error, 3.5 percentage points? Well, I just want to make sure I cover exactly the way we want it here. What's meant by the 3.5 is that it's highly likely, right? It's highly likely. It is highly likely that the percentage of voters supporting the Republican, you could do it either way, a Democrat or a Republican, supporting the Republican candidate is within 3.5% of the given 47%. The estimated 47%, right? So 47% is the estimate with a 3.5% margin of error. So it might be what? It might be 3.5 lower. It might be 3.5 higher. Okay. So what you're going to do here is calculate where did that 3.5% come from. Well, it came from our formula for margin of error of proportions. 2 times the square root of what was the percent? 0.47 times 0.53. 0.53 is 1 minus 0.47 divided by n. 800 was the sample size. And if you put that in your calculator, you get 0.035, which is approximately 3.5. It's exactly, not approximately, 3.5% margin of error. Okay, 3.5% margin of error. That's where that came from. So why did the poll director say it was essentially a toss-up? Well, let's think about it. If we had 47% as our guess, right? That's what they said would vote. Approximately 47% would vote Republican, right? 47% plus 3.5 is 50.5. Okay, that's even further away from Democrat, right? But 47 minus 3.5 is 43.5%. So what if it is 43.5%? What if it's 44? What if it's 44.5? What if it's 45? That's pretty darn close to the 45% Democrat. See? So because of that margin of error, it's too difficult to say that the Republican has this strong lead. They really don't. 2% difference with a 3.5% margin of error is nothing. It's a total toss-up. In fact, what if it is 43.5% And what if you add the 3.5% to the 45? What if you take the 45 and you add 3.5? Now you're at 48%. So it could be the case that it's 48.5% Democrat and 43.5% Republican. So now the Democrat's way higher than the Republican. With a 3.5% margin of error, it's too big of a margin of error to make any kind of prediction. That's why they're saying it's really just a toss-up. It's almost 50-50. So that's basically that. And then right here, we're talking about going to 2,500 voters instead of 800. So what's going to happen? We're going to increase the sample size, so you know that's going to decrease the margin of error. Right, okay, everyone said that, all right. So let's do it. Margin of error, now with 2,500, we're going to keep the same percentages instead of divide, but we're going to divide by 2,500 now, and that comes out to be 0.02. So 2% margin of error. Okay, 2% margin of error. Still, though, not enough to say it's not a toss-up. It's still a toss-up. Still a toss-up. Why? Same reason, and you could write this out. Take your 45%, take your 47%, subtract 2%. Subtract 2%, you're still at 45%. The 45% can go up to 47 with a 2% error, right? So with a 2% margin of error, they could actually flip-flop. The 47 can go to 45, the 45 can go to 47. Now the Democrat's ahead of the Republican. They could flip-flop just like that, or they could be equal. It is still a toss-up, even if you had 2,500 as your sample. So sometimes increasing the sample size is not going to matter. It's still going to be a toss-up. It did decrease the margin of error, but it's still a toss-up in this setting because the percentages were so close. All right. Last one here. We're going to talk about Nabisco Company, and we're going to save example 4 for class. The Nabisco Company claims that there are at least 1,000 chocolate chips in every 18-ounce bag of their cookies. So at least 1,000 chocolate chips in every 18-ounce bag. That's what they're claiming. So an article in a local newspaper reported that efforts of a group of students in their attempt to validate the Nabisco claim. The article reported that students randomly selected 42 bags of cookies. That's your sample size. From the grocery store, counted the number of chocolate chips in the cookies. Wow. So the students found the sample mean was 1,061.6 chips. So the average of their sample, so 42 bags, right? So some bags had this, that, they averaged them all out, and the average came out to be 1,061.6 chips. And the sampled standard deviation was 117.6 chips. Okay? So the article stated the students' data supports the Nabisco Company claim. Using the students' results, calculate the margin of error associated with the estimate of the mean number of chocolate chips in an 18-ounce bag. All right, so this time, because we're talking about a hard number of chips, it's not proportion, it's the mean. We already got the mean, okay? This is the mean. Here is our standard deviation that they calculated. So we're going to come up with our margin of error, and our margin of error is 2 times the standard deviation, right? And the sample standard deviation is 117.6. So remember, it's 2 times the square root. 2 times s over the square root of n. My bad. I wrote the wrong thing here. 2 times s over the square root of n. So 2 times s over the square root of n, and we said n was 42. Okay? So margin of error, calculate that. The margin of error is 36.3 chips. All right, so our margin of error is 36.3. Our sample is 1,061.6. So if we do 1,061.6 plus and minus 36.3, that's going to be a very, very good indication that of our give us a pretty good interval of the number of chocolate chips in the population, of where the average is. All right, so write a sentence interpreting the margin of error. So the population mean is likely to be between, and again, we just calculate these right here. One of them is, I'm just looking because I already did it, 1,025.3 chips and 1,097.9 chips. Okay, so do you agree that the student data supported the Nabisco company claim? Yes, since the expected number of chips is above 1,000, the claim is true. So see how our range, our likely range is between 1,025 and 1,097. It's in that range right there. So there's a very, very good chance that the average is in there. So we could say there are at least 1,000 chocolate chips in every 18-ounce bag of Chips Ahoy cookies. All right, so there we go. And we're going to do example 4 in class, and I will see you then.